So far, I hope that my discussion of vector spaces has been reasonable, and that we are kind of realizing that these vector spaces aren't so hard kind of at their core. And if you understand what's happening in, say, R2 and R3 and Rn, then you're going to be in good shape in here. Okay, we're not going too far outside the bounds of those things, but I did want to bring up some other ones so that you knew that the category of vector spaces was much larger than kind of you just think about it at first. So what I want to do now is give you a weird one, okay, where I'm going to define addition and scalable multiplication in a weird way and show you that it satisfies all of the axioms, okay? Now, here's what the example is. So let my vector space be R plus, and what that is the set of all x's that are positive, right? So this is the positive real numbers, okay? So we're going to define u plus v being multiply them, and ku being u to the k. So for example, 2 plus 3 in this vector space would be 6. And 3 times 2 would be 2 to the third, which is 8. Okay, now in this case, this thing is the vector, right? If I do 2 times 3, where 3 is the vector, that's 3 squared, which is 9. Okay, so weird things are happening here. Okay, so these are both vectors. This is vector addition. This is the vector. This is the scalar. All right, so if you do 1/2 times 5, that's going to be root 5, right? 5 to the 1/2. Okay, so there's kind of how this thing is going. What do I have to do? Let's go through all 10. First of all, if u and v are positive numbers, right, that's what v is, what is u plus v? Well, u plus v is, maybe we'll put a dot over that. That doesn't really mean plus, it's our new plus. That's u times v. Now, if you take two positive numbers and multiply them, you get a positive number, right? So positive times positive is positive. That is in R plus, which is V. So number one, check, right? When I add two positive numbers here, I get a positive number here. And by adding, I mean multiply. Okay. How about addition? Is it commutative, right? What is U plus V? Well, that's UV. What is V plus U? That is VU. Now, remember, I said over here 3 times 2 and 2 times 3 are different, but this is my fancy multiplication. Okay, that's my fancy multiplication. These are not fancy. Okay, those are just multiplying the two numbers, and those are in fact equal. Okay, so 3 plus 2 is 6, and 2 plus 3 is 6. Right now, I'm not proving it by example here. I'm already done with my proof, but that's what I mean, right? So if you do 7 plus 5 and 5 plus 7, those are both 35. Okay, very good. So 2, check. What about 3? U plus V plus W. Okay, so that's going to be U times, let me back up there. It's going to be U plus and then V times W, which is U times V times W. Now we're landing in the land of real numbers now, so that's the same thing as UV times W, which is UV plus W, which is U plus V plus W. Again, maybe I'll highlight the weird pluses. So those are all weird pluses. Cool. All right, 3, check. All right, there is a 0 vector. Okay, now the positive real numbers do not contain the number 0. So what is the 0 vector? Well, so that thing plus u has to equal u again. But by definition, what happens here is that I multiply them. So what number times u is u? And that answer is 1. So the 0 vector is the number 1. So u plus 1 is u times 1, which is u. So the 0 vector is the number 1. And at this point, our minds are blown, right? Like this is something really weird is going on here. So again, the 0 vector in this land of positive numbers as a vector space is the number 1. Okay. Now, for every u, there's a minus u. Okay, so if I take a u and I add it to something else, I know that's going to be u times the thing, and I have to get the 0 vector. And so that means that u times that thing is equal to the number 1. So what is that thing? Well, that thing is 1 over u, right? 1 over u times u is 1. So the additive inverse is 1 over u. So u plus 1 over u is 1, right? How about 1 over u plus u? Well, that's 1 over u times u, which is 1, which is the 0 vector, okay? All right. So that means that, let's just pick some numbers here. So 2 plus what gives me, well, 2 plus 1/2 is 2 times 1/2, which is 1, which is the 0 vector. Okay. So this thing is the additive inverse of that one. And I might add here, this does get along with the things that we already know, because if I have -1 times 2, that is 2 to the -1, which is in fact 1/2. So that's good, right? That gets along with our other operation as well. Next page. So if k is a scalar and u is a positive number, then ku is a positive number. Okay, so k is any scalar times u is u to the k. Now, if I take a positive number and raise it to any power, what do you get? Well, you get a positive number. Okay, so that's good. Even if k is negative or whatever we want, we know that any positive number to any power is going to be positive, right? So even if you want to think about like what is, -3, that number times the vector 5, well, that's 5 to the -3, which is 1 over 5 cubed, which is positive, right? So this works for negatives, it works for fractions, and all that. All right, so number 6, good to go. Number 7, okay, let's do this here. So k times u plus v, that's k times the number uv, which is uv to the k. All right, now here I'm in the land of real numbers, so this is going to be u to the k, u to the v. I'm sorry, not u to the v. U to the k, v to the k, which is u to the k plus v to the k, which is ku plus kv. Okay, we're there. See, this is fun. I'm having fun. All right, what about this one here? Now, the thing to point out here is that this is our new fancy vector addition. This is just regular addition, okay? So maybe I'll put a highlight on the fancy addition, and the other one is not. So let's go with the right-hand side here. So on the right-hand side, I get u to the k plus u to the l, which is u to the k, u to the l, which is u to the k plus l. Oh, and there we go. That's k plus l u. There we go. Number 9, k times l u is k times u to the l, which is u to the l to the k. Now I know what I can do with these is multiply those, so that's u to the lk. Oh, I see, I need them in a different order. That's fine. So that's u to the kl, which is kl u. Check, number 9. And number 10, let's see, 1 times u is u to the 1, which is u. All right, number 10, check. Okay, so that was an intentionally weird example, and you know, maybe go back through that. I did that one just to kind of show us that this whole idea isn't just sort of silly. That there's a lot more to it than we kind of think, right? Think of this kind of like you know, the harmonic series, right, where it does something kind of unexpected. And I think that this is kind of one of those things too, where we don't really expect all the things to just work out. And hopefully you kind of followed the symbol pushing here. Again, I'm not going to ask you to do this kind of thing for me, but I did want you to see it before we move on. Okay. And then the next thing we're going to talk about is subspaces, and I'll see you then.